Welcome to our presentation on the development of an autonomous tennis ball collecting robot. As the technology demand grows in the application of sports and recreation activities, the autonomous tennis ball collecting robot was proposed with the goal to improve training efficiencies of tennis sessions, providing athletes with a more enjoyable experience. The aim of this project is to develop an autonomous tennis ball collecting robot, which uses computer vision to detect tennis balls through cameras. The product is intended to be used at the end of tennis sessions, where we'll scan around the field, locate and collect tennis balls inside the current court area. The picture shows the mechanical concept of the platform. The front side of the robot is isolated using acrylic plates for holding on the electronic components. And the back side acts like the storage for tennis balls. When it drives towards the tennis balls, the balls will be guided into the side tunnels of the robot and will be picked up by the friction of the wheels, as shown in the pictures below. Such design made a few innovative improvements from previous similar projects. The unibody design is compact and space efficient. The power transmission system is relatively simple, with only 2 motors needed for both motion control and ball picking function. Lastly, the design took consideration of real-life applications. With the extra large wheels on both sides, the robot is capable to maneuver in both indoor and outdoor environments. On the electronic side, 2 single-board computers were considered for this project, including Raspberry Pi 4 and Jetson Nano. These 2 have similar common specs in terms of I/O ports, processing power, and operating systems. However, Raspberry Pi does not have a GPU, which could make a critical difference when it comes to machine learning and neural networks. On the other hand, Jetson Nano has official robotic projects run by NVIDIA, which proves the feasibility of it being used in similar applications. Hence, for future-proof considerations, Jetson Nano was selected as the controller for this project. The Jetson Nano boots on automatically when plugged into power. However, there was a little confusion about how we can get the board running on the robot, and how does that differ from being plugged into keyboard and mouse for programming. The initial idea was to set up a run-on boot script, which we can manually exit if we want to program it when plugged into on the table. Later, we found an easier approach to remote access the chip using Secure PowerShell and Jupyter Notebook, which enabled us to achieve remote real-life control and modification on the platform anywhere with a mobile device. For computer vision, a blob detection test was carried out using a webcam. With color contrasting on the blue and red channel of the image, the clusters are then filtered with a defined pixel count window. Any clusters passes the filter window will be seen as a detected ball. The color and size threshold values can be adjusted, shown in the bottom left picture. And the bottom right figure shows the output format of the function, with the coordinates, dimensions, and pixel counts of the detected balls. Shown here is the circuit of the electronics. An Arduino is powered in parallel alongside the Jetson Nano using 12-volt power supply, where the Jetson Nano has the power step down from 12 volts to 5 volts using the regulator. The 6-pin connections between the Jetson Nano and the Arduino encodes a series of motion commands corresponding to different ball positions, as shown in this image. Upon experiment, it was found that the signal sent by the Jetson Nano was very weak and noisy, as you see in the upper figure. This issue was solved by voltage step-ups using transistors, and then improved result is shown in the lower figure. The data shown here were measured using analog pins on the Arduino in order to indicate the noises. However, in real life, we'll be using digital pins for better indication. The illustration shows the setup for a pin connection, where the battery represents the power pins on the Jetson Nano. The operation logic is shown in this flowchart. The robot will drive towards the closest ball detected, which is defined by the highest y-axis value on the list. If no balls are detected, the robot will search for all other directions before going into sleep mode, waiting for further commands. Thank you very much.